Good morning all of you. In this video we try to understand speed control of a DC shunt motor. So we can control the speed of the DC shunt motor with help of two methods. One method is field flux control method. Second one is armature control method. So first we try to understand how we can control the speed of the DC machine, in fact DC motor, with the help of field flux control method. See here, this is the DC motor for which we want to control the speed of this motor. So in this field control method, this is the field winding. So in the field flux control method, what we do is, see, actually if there is no resistance, this variable resistance R is not there, then the current flowing through the field winding is constant, that is ISH. So as field current is constant, the flux phi is also constant in a DC shunt machine. So in order to change the flux, what we are doing is we are inserting a resistance in series with the field winding, and we are gradually increasing the resistance. As the resistance is increasing, see, the field winding resistance increases, so ISH will decrease. As the field current is decreasing, the flux produced in the field winding due to this field current will reduce. So the flux phi will reduce. As the flux decreases, the speed of the motor increases, as the speed is inversely related with the flux. So as the flux decreases, speed will increase. So now let us try to understand point by point. See, the flux produced by the shunt field winding depends upon the current flowing through it, that is ISH. So as the ISH is equal to V by RSH, see here in the diagram, if you observe, this current flowing through shunt field winding is nothing but the voltage applied at the terminals of the motor. The terminal voltage applied to the motor will come across the field winding. So V divided by RSH is the field winding resistance. Earlier there is no R, we inserted this variable resistance R or a restart. Okay, so this ISH is nothing but VT by RSH. So based on this ISH, the flux will be changing. If ISH is constant, flux is also constant. So in order to change the flux, we have inserted a resistance R, that is variable resistance. So we can change the resistance value of this variable resistor. Okay. So let us try to understand the second point. When a variable resistance R is connected in series with the shunt field winding, the shunt field current ISH becomes V by RSH plus R. This R is the variable resistance that we added. Okay, so because of this, the shunt current will reduce, hence flux also will reduce. Consequently, what will happen? The motor runs at a speed higher than the normal speed. So as the flux decreases, speed will increases. That's why motor will rotate at a speed above the normal speed or above the rated speed. So the amount of increase in speed depends upon the value of the variable resistance. So the speed variation, how much is the increase in speed, depends on the how much value of the resistance you have inserted in the shunt field winding. Okay. So now let us try to understand. See, if I draw torque versus speed characteristics, as the torque increases, the speed is not changing in case of shunt machine, but at different values of flux. See, this is the rated flux phi the motor is rotating at a normal speed or a rated speed. This is the normal speed or the rated speed. As I am inserting a resistance in series with the shunt field winding, as the flux is decreased from phi to phi 1. If the flux is decreased, speed will increase. That's why see speed increases from normal speed to more. Means we are running the motor above the rated speed now. If I decrease the flux further, how we are decreasing the flux further? By increasing the resistance R. The speed will further increase to this point. So in the field control method, we can control the speed of the machine above its rated speed or normal speed. I hope it is clear. Now let us try to understand armature control method. See, in this armature control method, the speed is directly proportional to induced EMF EB or the back EMF EB. See, in a shunt motor, flux is constant when applied terminal voltage and shunt field resistance are constant. Here if you see, there is no resistance inserted in the shunt field winding, so the shunt field winding is fixed at RSH. And if I fix the terminal voltage what I am applying to the motor, then Vt is constant. Then there will be back EMF developed across the motor terminals. That EB is given by Vt minus Ia into Ra. Ia is the current flowing through the armature of the DC motor. Ra is the armature resistance. So as the N is directly proportional to EB, if I am able to change the back EMF EB, I can change the speed at which the motor is rotating. So in order to do that, what I am doing is, see, anyhow this terminal voltage is not changing, Vt is constant. So if I want to change this Ia-Ra drop, I can change Ia-Ra drop by changing this armature resistance Ra. For that, what I am doing is, I have inserted a variable resistance R in series with the armature. As the armature resistance increases, this Ia-Ra drop increases. Because of that, V minus Ia-Ra. If it is increasing, the overall value will decrease. So back EMF is decreasing. As the back EMF is decreasing, the speed at which the motor rotating will also decreases. That's why when a variable resistance is connected in series with the armature, the induced EMF EB, which is equal to V minus Ra plus R. This R is the external resistance that we added in series with the armature, is reduced, and hence the speed also reduces. As the back EMF reduces, speed also reduces. Thus motor runs at a speed lower than the normal speed or rated speed. So generally armature control method is used to control the speed of the DC motor below its rated speed. See, for example, without resistance the motor is operating at a speed n0, which is the nominal speed or rated speed. So as you insert a resistance R1, the speed decreases like this. If you increase further the resistance in series with the armature, then speed further reduces. Okay, I hope it is clear. So I would like to stop here for today. Thank you all for your patient hearing.